Hello, everyone. I'm Jason Dai from Intel Software and Service Group. So in this session, I'm going to talk about how we use the Spark Stack to build the next generation of big data analytics, the real-time analytic processing. And first, some background. We all know that the Spark Stack is based on the research open source project initiated by the AMP Lab in UC Berkeley, which in my mind has done a fantastic job of building the open source next generation analytics stack, the badass, the Berkeley data analytics stack. And Intel has actually been working very closely with the AMP Lab and as well as the community on the open source development of the Spark Stack for a couple of years. And the Spark Stack goes into the Apache incubation since this June, and by the statistics, it is the most active cluster data processing engine after Hadoop MapReduce. In addition, we at Intel have been actually collaborating with many big websites, especially some of the very big, large websites in China, such as Alibaba, Baidu Qi, Youku, and so on, to build the next generation big data analytics applications using the Spark Stack, which we believe represents a general trend toward the real-time analytic processing. So what exactly do we mean by the next generation big data analytics? Well, I mean, by now everyone should be familiar with all the 3 V's or 4 V's of big data, so I'm not going to bother you with that. I think the point here is that there are many different aspects of big data applications which actually represent different challenges. I mean, you may have a larger volume of data. You may have data coming from many different sources in many different formats. But the key point here is that you want to extract values from your data. And to do that, you need to run various analyses. And from our point of view, those analyses can be roughly categorized into 2 classes. One is more like SQL query, which we call it simple analytics. You're doing all those ETLs, joins, aggregations, cube materialization, drill up, drill down, so on and so forth, which try to describe what happens in the past, the so-called descriptive analytics. And the other type of analytics really involves those it does not look like a query, the SQL query. It involves very complex mathematical operations, linear algebra, graph analysis, and so on, which try to build a model to predict what will happen in the future. In addition, as the big data applications become more pervasive, there is increasing demand for the real-time analysis. And again, I think there are 2 different types of focus here. One really focuses on the latency between you issue a query to when you get a result back, the interactive analysis. And the other type, the streaming processing, which you have a lot of events coming into your system continuously. And the focus here is really try to minimize the latency between when the event happens to when the effect, the impact of the event is reflected in your analysis result. And we believe the Spark Stack actually provides a solid foundation, that's a great technology for us to build the new types of complex and real-time analytics, and which we believe represents a general trend to the real-time analytic processing, which essentially is our vision for those next generation big data analytics. So in this paradigm, you have a lot of events or logs which coming into your system continuously, and so the real-time data will need to be captured and processed and consumed in a semi-streaming or online fashion. In addition, so the real-time data and history data will need to be combined and mined interactively and iteratively. For instance, maybe you want to do some very complex OLAP business intelligence style analysis in interactive fashion, or you want to run some very complex iterative machine learning graph analysis algorithm on top of that. And also importantly, a lot of those processing data storage will be memory-based in this paradigm. So this is our vision for the next generation big data analytics. So next, maybe we should look at some of the real-world use cases, which is not quite there, but actually represent some of the general trend towards this real-time analytic processing. So first use case is actually a pretty simple but very common use case, real-time log aggregation or semi-real-time log aggregation. So you have a lot of agent or maybe your front end which collect logs, continuously collect logs and streaming the log into the system, typically through some queuing or messaging system. And those incoming logs are processed in a semi-streaming fashion. It typically performs various aggregations along different dimensions, time period, demographic, and so on. And when necessary, so you will join the log with the history table, the real-time log and history data when necessary. And the aggregation result will be consumed in a semi-online fashion for monitoring, for instance, alerting, and so on. So this is a real application we actually have built for one of our users. You have, so essentially this chart here shows the general architecture. So you have a lot of the log collected which runs maybe alongside your web server or anyway, alongside the agent. And then the log collected are essentially implemented as a Kafka client, which gets the log data and publish it to the Kafka continuously. And then we run the Kafka server and the Spark server on the same cluster. So the Kafka server and the Spark cluster are co-located. And at regular intervals, an independent Spark job is launched, which gets all the recent data, all the latest data in the Kafka server and process the data. So it's essentially the application is implemented as a series of mini batch Spark application run, and it's running in the fine-grained mode of methods. I will come back to that later. And the jobs, each job, so for instance, every 10 minutes, every 10 seconds, or maybe every 15 seconds, you will launch a new Spark job which will process the newly received data, which typically does various aggregations and then write a result out to some external, in this case, RDBMS system. So this simple architecture, this simple application is currently in production at the user's environment for several months, and it's running pretty well. And currently it's run at tens of seconds latency. You can actually scale that to lower latency, but the users are pretty happy with that. So some of the design decisions we have made in our application, essentially, first we co-located the Kafka and the Spark servers. And then for each Spark job, we actually implemented a customized input format for the Kafka, so that for each distinct Kafka partition, we will launch a distinct Spark task. And the Spark task will always read from local Kafka server, and typically, because it only reads the latest data, it typically read from the local file system without touching the disk. So typically, the data read from the local file system cache. And we implemented the application in such a way that at a regular interval, a standalone, an independent Spark job is launched. And the job, the application will first log the current offset of the specific Kafka partition in Zookeeper, and in case a job fails, we just discard that batch of data. There are other ways to do maybe more complex fault tolerance, but well, this simple scheme works well for our purpose. And the Spark jobs, the Spark class is running in fine-grained mode on methods. So the difference here is that if you run there are several choices how you can run the Spark job today. You can run it in standalone mode, in YARN mode, on coarse-grained mode, on methods, which essentially means that you have a dedicated Spark job which will take all the resources it has, and then it will release the result after the job is done. So the fine-grained mode is helpful here in that it allows multiple Spark jobs to actually Spark context actually to share the results in a fine-grained fashion, so that as long as you have a task finished, you can release the result for the task, which is actually handy because because it's around a series of Spark jobs. So when a previous job actually is delayed for whatever reason, maybe there is a issue on the server or whatever, so it's running longer than its batch time. The next job will come around, but it still can find the results to run. Whereas if we run in a cost green mode, you essentially currently you need to wait for the previous job to finish before the next job can get any results. So in terms of performance, the input, the log collection part is actually bottlenecked by the network currently. And we are using 1 gigabit Ethernet, so it's maxed out our network connection. And the processing, the Spark job side is actually bottlenecked by the CPUs because we always read data from local file system cache and doing the processing and doing some various aggregation. So it's actually currently bottlenecked by CPU, and it can easily scale out by adding more servers to speed that up. I think without any tuning, we can actually scale that to maybe several seconds latency. So our implementation is actually based on running it on independent Spark jobs. So we can potentially run it in Spark streaming. Actually, this is what we are currently working on, migrating the application to Spark streaming, which the framework will provide better streaming support. For instance, it allows us to do complex stateful analysis, provide better fault tolerance, and so on. But when we migrate to Spark streaming, we actually no longer co-located the Kafka cluster and the Spark cluster, because in Spark streaming, if you are familiar with the abstraction, the D streaming in Spark streaming will retrieve the data in background and over the network and cache it in the local memory. So there are no point to co-locate the Spark and the Kafka clusters. And again, I mean, in Spark streaming, it will cache the data in memory, so a lot of effort actually have been spent on the memory tuning to reduce the GC, to clean up the metadata and so on. But it gives us even lower latency, because in this case we can reuse the Spark context, which reduces the startup overhead. Actually, there's no startup overhead in this case, so we can actually reduce it to, I think, a couple of seconds latency. So that's a real-time log aggregation. The next use case we are working at really about is really on those very complex OLAP analysis in an interactive fashion. So we use Spark and Shark to significantly speed up the ad hoc complex OLAP queries. So essentially, we run a Spark Shark cluster alongside a existing Hadoop Hive cluster. So in a lot of our use cases, the user already have a Hadoop deployment. They collect their data into their HDFS or maybe Hive data warehouse. And to speed up the queries, we run a independent Spark cluster alongside the Hadoop deployment, so that we do not necessarily no ETL or storage overhead but we can take advantage of Spark to significantly speed up the queries. And in a lot of cases, we also take advantage of the in-memory primitive in Spark, so that we load the data of interest into memory. In this case, we load it into a Shark table, and then run various analysis on top of the in-memory data. And in this case, a lot of time, the analysis is front-ended by a lightweight UI, which does all kinds of data visualization and exploration. So in this particular example, I'm going to talk about is really about how we perform those complex analysis on the time series data we are collecting. So essentially, the input data is a time series, which you have a timestamp, a object ID, and a event ID associated with that object. For instance, you can think this is maybe you watch a video by a specific user, or maybe purchase a stock by a specific account, and so on. And the output here is we try to compute the unique event count for each time range. So in this case, for each object, you want to compute in a specific time range the unique event of that object, and the unique event that happen at least twice, and so on. And the time range can be, for instance, in our case, we often compute the statistics for the time ranges that aggregate the time. For instance, we compute the statistics for the first day of the week, the first 2 days of the week, first 3 days of the week, and so on. So it's essentially accumulate all over the time, the time ranges for the event. And what we have implemented, it's actually a simple two-level aggregation implemented in Spark. So the unique thing about it is it's actually leverages several properties in Spark which makes it more efficient, including how you implement a specialized partitioning, how do you utilize the general execution graph in Spark to do the two-level aggregation, how do you cache the data in memory, and so on. And the result is that the original implementation is actually run on I think it's a 100-node Hadoop cluster for about 20 hours. And we are able to run it in several minutes on a 4-node Spark cluster, utilizing a cache. So this is how it works. So you have input data series and the timestamp, the object ID, event ID. You first map the timestamp to a specific day in the week. So you convert the timestamp to a number from 1 to 7. And then you do an aggregation shuffle. Essentially, you compute the, for each day, how many occurrence of that event for each event. And this data is partitioned by the object event ID and potentially cached in memory so that you can compute various statistics over that aggregated data on the fly. So, for instance, to compute our output, the event occurrence for each time range, what we do first, essentially we aggregate the occurrence of that event across the time range. Because the data is actually partitioned by the object ID and the event ID, this is a local aggregation, no network, no shuffle is involved. So it's actually pretty fast. And then once you compute that, you can actually generate it actually looks like a word count. You essentially generate for each object ID for the time range, whether the event happened once, or whether it happened twice, and so on. And finally, you aggregate across all object IDs, and you can compute the final result. So the result is essentially for each object in that specific time range, how many unique events happen at least once, happen at least twice, and so on. So the whole flow actually runs in a couple of minutes, and and we can easily we did some analysis. We can easily scale that to maybe tens of seconds latency. And the third use case we are talking about is really about the very complex machine learning and the graph analysis, which involves a lot of the complex mathematical operations. It's mostly matrix-based, doing all kind of multiplication, factorization, and so on. Sometimes it's graph-based if it's a sparse matrix. And also, a lot of those algorithms are very iterative algorithms. You just run it iteratively until it converges. So it's you want to cache the matrix or graph in memory across those iterations. So one specific application we are working on in this case is a n-degree association in the graph. So it's essentially computed association between two vertices that are n hops away. Maybe you think of it as maybe a friends of friends or something like that. And the formal definition is given here. So the first degree of weight is essentially the weight on the edge, which is between 0 and 1. And the n-degree association is defined recursively on that. And we actually implemented a graph parallel implementation on top of Spark using both Bagel, which is basically a pre-grade implementation on Spark, as well as the GraphX. And again, a lot of effort is spent on the memory optimization to try to cache the graph efficiently. And the result is that previously it actually runs on again on a 100 node Hadoop cluster for over 20 minutes, and we can scale it down to less than 2 minutes on a 4 node Spark cluster. So this is how it works. So you have a vertex and an edge in your graph. Each vertex you maintain its state. The state essentially is the current top k weights to the vertex. So essentially, you compute the weight from vertex x to u, and you store that on the node u. And we cap it on the top k because once you run several iterations, the graph becomes extremely dense and it just runs out of control. So for our practical purpose, we just cap it at the top k. So initially, each node contains the self weight. I think so. So initially, the graph initialized as each node contains the weight. So for on vertex u, it only contains the weight from u to u, which is 1. And then for each iteration, what it does essentially it sends a so it computes the new weight to its neighbor by multiply so on node w it computes it stores all the weight from x to w and multiplies that weight from w to u. It actually computes the n+1 association from x to u and it sends it over to node u. So every node does that for its neighbor. And when the node receives all those messages from its neighbor, it's actually aggregated across all the messages and then computes the new weight, and it's actually, again, kept at top k. As I mentioned, we want to control the density of the graph. And you just iterate until you get to, so in the first iteration, essentially everyone, in the initial iteration, everyone maintains the weight to itself. In the second iteration, in the first iteration, you have a first one degree association, and you just iterate so that you iterate n times, so you get an n degree association. So in this case, we can actually utilize the graph layers built on top of Spark to efficiently compute those graph analysis. So, okay. So see that the three different use cases that we are working on at Intel with our users, especially those big websites. And along the way, we actually have contributed a fair amount of code and functionality to the Spark stack. And we will actually continue to do that. And so in summary, we actually have been showing a few real-world use cases, which we think represented the general trend to those next generation of real-time data analytics. And we see the Spark stack actually provide a great foundation for those new applications, new big data analytics. And it actually has a very active community and has a lot of new components, new layers, new frameworks that coming up, SQL streaming, graph, to name a few. And well, we at Intel actually are happy to collaborate with our users and the community to build those next generation analytics application using Spark stack. So that's all I have. Thanks.
Thank you, Jason. So we do have time for one question.
Hi. So actually, when you said you have the graph algorithm, you got speed-ups compared to Hadoop. So were you implementing it on top of Hadoop, or you took either Giraffe or Hama or something like that, and then you compared with that?
We didn't implement Hadoop versions. The user actually has a version running Hadoop, as well as actually they also have a version runs on a single node, which they reduce the size and keep everything in memory to compute. So the Hadoop, I believe that it's essentially a plain Hadoop implementation without utilizing those frameworks, new frameworks. But our result, our cluster result is about the same. Actually, it's faster than the single node implementation utilizing all the memories. They have custom implementation as well. Okay. Yeah, but we do not compare to those giraffe new stuff.
All right. Thanks again, Jason.
Yeah.